Today we're going to learn about U-Substitution, and it's really going to open up the library of functions that we can anti-differentiate. Now, it's really kind of only useful in a limited sense, but it will allow us to integrate a whole lot more. And then in the spring, when we get a product rule for anti-differentiation, that will really open it up. But for now, this is going to really help. So we're going to start by taking some derivatives using the chain rule. So I'm going to ask those of you in class to do this on your own. If you're watching at home, you can just watch as I do it. Okay, and so really what we're doing today is we're recognizing situations where a function could be the derivative of something else after use of the chain rule. So, notice here that here we have multiplication by g prime, and g is the inside of the function, and we're seeing its derivative. See, we've got the inside, we've got an interior function, and its derivative. An interior function and its derivative, and, an interior function and its derivative. Okay, once we start to recognize that pattern, when we're asked to anti-differentiate something like that, we'll know that we need to use U-Substitution. Okay, first we're going to find an antiderivative for cosine of 3x with respect to x. Now this is one that this year I asked y'all to do in the previous unit. Okay? In the past I had kept it relatively light when we first started anti-differentiating, but I'm expecting a little more of y'all this year. Maybe because I had you in pre-cal. But so I think that you could cook up an antiderivative for cosine of 3x. Anybody got a hypothesis? Yeah, sine of 3x times 1/3. So really what we've done here is we've prepared a place for this 3x to come out when we take the derivative using the chain rule, and then cancel out because we need one cosine of 3x. If I've forgotten anything, I have. Yeah, I forgot a plus c. Okay, we want an antiderivative, so that's a class of functions, all separated by constants. Okay. Now we're ready to really jump into it. So today we're going to develop a technique for anti-differentiating composite functions. And really, this is the pattern you want to recognize. We want something with the inside, with an inside, and then you see its derivative on the outside. Okay, we're looking for something, in practice, you're just looking for something being the derivative of something else. Okay? Or at least related. If you let u equal g of x, then u dx equals g prime of x, right? Take the derivative with respect to x. And then you multiply both sides by dx, and you get du is equal to g prime of x dx. And then you substitute on dx. Okay. Because dx, in this case, is equal to 1 over g prime of x multiplied by du. So when we substitute that in, right there, it's going to get rid of the g prime. G of x is u, and f of u du is something we're more likely to be able to take the antiderivative of. All right, both of these top two examples I don't really like as much. They're not just perfect for it. So I'm not going to do these right now. I'm going to come back and do them in a couple minutes. Okay, let's go back to this first example. And we're going to solve this using a U-Substitution. What we're going to do is we're going to let u equal 3x. Okay, then then du dx is equal to 3. Meaning du equals 3 dx, and dx is equal to 1/3 of du. Okay. Now I'm going to actually substitute on dx. So now I have the antiderivative of cosine of 3x is u, and dx is 1/3 of du. So this is 1/3 of cosine of u du. And then you think, okay, well, what's an antiderivative for cosine of u with respect to u? Well, that's sine of u. Plus c. And then the very last step is we substitute back on u. So that's 1/3 of sine of u is 3x plus c. So that was a nice, easy example to get us started. All right, here's another one that is prime for U substitution. All right, so I'm seeing that 4x to the third is the derivative of x to the fourth. So it's like, okay, I'm going to use U substitution on this. And so what I'm going to do is I'm going to let u equal x to the fourth. Then I'm going to take the derivative, du dx is equal to 4x to the third. And that means that du is 4x to the third dx. And then I am pretty much a subscriber to the solve for dx technique. Used to, when I learned, they said just match it up or just figure it out or something, but we know that doesn't work that well anymore. And so I'm going to say dx is equal to 1 over 4x to the third du. So now what this is the antiderivative of 4x to the third sine of, wait a second, x to the fourth, that's u. And dx is du divided by 4x to the third. And so I'm going to get rid of these things. And then you'll know you're ready to move forward, or you've substituted correctly, when all of the x's are gone and you're left with just u's. Okay, so this is equal to the antiderivative of sine u du. And I know an antiderivative for sine. That's going to be negative cosine of u plus c. And then the last step is we substitute on u. Negative cosine of x to the fourth. 4 to the x plus c. So that one worked out pretty well. All right, well, what about this one? I know that the derivatives of tangent and secant are, kind of related to each other. Are we seeing something that's the derivative of something else? Not exactly. Do we maybe just know an antiderivative for this one? Yeah, okay, so not all antiderivatives that look kind of challenging require U substitution. This one is just secant x plus c, right? All right, so I think now it would be good for us to do a couple of definite integrals using U substitution. All right, so I don't see anything that's exactly the derivative of something else, but we don't need them to be exactly the derivative. We just need them to be related or just off by a constant. So if you take the derivative of the inside of x squared plus 2, you're going to get 2x. And 2x is not the same as x, but it's only off by a constant multiple. So what I'm going to do is I'm going to let u equal x squared plus 2. So du dx is 2x. Du is equal to 2x dx. And dx is du over 2x. Since I have x's as my bounds of integration, that should really say x equals 0, right? And x equals 2 is what we mean. I need to change this whole integral into terms of u. So what I'm going to do is I'm going to make a little table of values. X and u. Okay, so my x values I'm interested in are 0 and 2. And we get u from x by squaring x and then adding 2. So 0 squared plus 2 is 2. 2 squared plus 2 is 6. So now this becomes the same as the integral from u equals 2 to u equals 6 of x times the square root of u. dx is du divided by 2x. Yeah, see the x's are canceling each other. And I'm left with an integral entirely in terms of u. So really what this is, and then the divided by 2 I can factor out into the front. So that's half of the integral from 2 to 6 of u to the 1/2 du. Right? Well, what I'm going to do is I'm going to set up the power by 1, so that's u to the 3/2, and then divide by the new power, so that'll be 2/3. And we're going to go from 2 to 6. So this is, and at this point, I kind of like to factor out the 2/3 as well, because the 2/3 will be present when I plug in 6 and when I plug in 2. So I'm going to factor that out, and I'll be left with just 2/6, or 1/3, of 6 to the 3/2 minus 2 to the 3/2. And that's a safe place to stop. That's just a number. All right, so here's one I want you to try on your own. If you're watching this at home, I would recommend pausing the video, working it, and then checking your circuit spine, because in about 10 seconds it's going to just flash the answer. All right, here you go. See, I used u equals 2x over 3, which is the same as 2/3 of x. So du dx was 2/3, so dx was 3/2 of du. I converted the units, I switched into u's, and then I just integrated like we did last time. Next we have some questions that are, well, they're related to certain questions I've seen asked on multiple choice items before. All right, so they're saying the integral from 4 to 9 of f of 2x dx equals 6 and u equals 2x. What would be the equivalent definite integral in terms of u? All right, well, u equals 2x. First thing I'm going to do is I'm going to change the bounds from x's to u's. That should be pretty easy. 4 to 9, we're just going to double those. That's 8 to 18. Yeah, this is ripped straight off of a multiple choice question. I can just picture it. So now what I'm going to do is I'm going to say, well, u equals 2x means du dx equals 2, and then du equals 2 dx, and dx is half of du. So when I go to make the substitution, this integral is going to become the integral from 8 to 18 of f of u, then multiplied by, well, dx is half of du. And now that's, equivalent to the right answer, but I expect that if it was a multiple choice item, it would look more like this. And then if u was the square root of x, that's x to the 1/2, u dx is 1/2 x to the negative 1/2. Okay, so I could say that du is equal to 1 over 2 times the square root of x. I'll show you how we used to do it. You tried to match up what you have. I have a 1 over square root x dx right here. So I'm going to try to make that happen over here. The only thing that's in my way is this 2 in the denominator. So I'm going to multiply both sides by 2. And I'll get 2 du equals 1 over the square root of x dx, okay, which is what I had set out to substitute on. And now I've got something that matches up. So I'm going to say, oh, and I need to first convert my units. U is the square root of x, so that's 1 and 2. All right, so that's equal to the integral from 1 to 2 of e to the u, and then I've substituted on the divided by square root of x and dx, and I'm left with times 2 du. So that's another way of going about it, if that's how you see it. But I find the solving for dx and canceling out x's to be really the best way to go. No doubt. Here we have another question that is definitely similar to something you're going to be faced with on a quiz or a test or something. And these can be a little tricky. But again, my recommendation is that you just go ahead and follow the same process. Okay, so I know that u is going to equal 5x, meaning du equals 5 dx, or dx is equal to 1/5 of du. And change the bounds, x's to u's. 1 and 3 goes to 5 and 15. All right. So I'm going to work just with, I am only working with this integral, okay, which I know is equal to 10. So this is the same integral as the integral from 5 to 15 of f of u. And then dx is 1/5 of du. And then we know that that's equal to 10. So 1/5 of the integral from 5 to 15 of f of u du is equal to 10. But that's not what we're interested in. We want to know just the integral of f of u du is equal to c. And that's where you could get tripped up on this problem, I think. So where the first time I saw this problem, that was really confusing to me. Okay, so remember that we are just solving for that, which is really just this part, right? So I'm going to multiply both sides by 5. So I've got the integral from 5 to 15 of f of u du equal to 10 times 5 is 50. Meaning that a is 5, b is 15, and c is actually 50. All right, the last one I've got for y'all, I'm changing this to a definite integral from 1 to e to the 6th of 3 over 5x dx. First things first, I need to rewrite this. Oops, we lost focus there. And that's going to be equal to, I'm going to factor out the 3/5. 3/5 of the integral from 1 to e to the 6th of 1 over x dx. I realized that we didn't do any of these last time. Okay, what's an antiderivative for 1 over x? Log of, yeah, the absolute value of x, yeah. So this is going to be 3/5 of the log of the absolute value of x evaluated from 1 to e to the 6th. So this is 3/5 of the log of 1 minus the log of e to the 6th. Both of these are things you're expected to be able to evaluate. What's the log of 1? Yeah, and the log of e to the 6th? Yeah. And then I'm going to plug that in, subtract, and get myself an answer. And there it is. All right, I'm going to actually do one more. But before I go on, I'm going to just let you know, I've been alerted that an earlier example I did contained a major error. It was the one that was like cosine of 2x over 3. I made an arithmetic error when converting the bounds. I said that pi over 2 went to 3 pi over 2, when in reality it went to 2 pi over 3. And nobody took the time to alert me to that, and so the entire example is botched. What I'm going to do is I'm going to record a separate video tomorrow in my 5th period class. I'm going to remove this video from the internet, and yeah, please don't judge me for making an arithmetic error. All right, the last one I've got is 1 over x log x. Well, I just got to say, what is the derivative of what? Okay, this is like 1 over x times 1 over log x. Okay, 1 over x is the derivative of log x. So I'm going to say I'm going to let u equal log x. And then du is 1 over x dx, meaning that dx is x times du. Okay, I need to convert the bounds from x to u. It's e and e to the 2. Okay, the log of e is 1, the log of e to the 2 is 2. All right, and so I have the equivalent integral is the integral from 1 to 2 of 1 over x times 1 over log x is u, and dx is x du. And so x's are gone, and I'm ready to proceed, you know. I've got the antiderivative of 1 over u is the log of the absolute value of u. So I plug in 2, I plug in 1, and I get log of 2 minus the log of 1, which is 0, and then I'm happy. All right, and that's all I've got for you.